Okay, so let's draw a moving object or a train to sort of capture the ideas of the famous thought experiment of the lightning bolt on the moving train, or, well, I guess we can. It's not a lightning bolt if the light that's produced is produced by the person that's on the train. So let's say the person here's our moving train or vehicle, whatever it is, a bus. And there's we look at this from the perspective of someone who's on the moving object, and this person is standing right in the middle and turns on light, and we can think of it as particles of light being emitted from that location and traveling in all directions. But what we care about is the direction to the right and the direction to the left. And so here's the light traveling outwards, a light ray going to the right and a light ray going to the left. If we look at this from the perspective of the observer on the train or experimenter on the train, then this particle of light hits this wall as this one hits the back wall, right? So they're simultaneous events from that perspective. But if we look at this from a different perspective, so we're off the train and we look at what's going on the train, and we see that the train is moving that way, and the speed of light is the same in all in all directions from our perspective as well, right? That's the foundation of the theory. Then what we would see is that we would see something like this, right? That when the particle hits the back part, the front part hasn't received its particle of light, right? That particle of light has not hit the front part because the back part is moving toward the beam of light, toward this one, and this part is moving away from this one. So they're not simultaneous. Okay, so we want to get a sense of what this looks like on the space-time diagram. So let's look at this from these two perspectives on the space-time diagram. So x and t, and from one perspective, the train is not moving. And so let's put the middle of the train right here. And so if the train has length, let's say the length of the entire cabin there is L, then this would be, well, let's just call this is some x naught, and this would be some x naught plus L over 2. And the back of the train would be x naught minus L over 2. Okay, and so the front of the train looks like this on the space-time diagram. It's just moving in time because the train is stationary from that perspective. And so when we do the experiment from the perspective of the train, we launch a particle of light forwards. What does that look like? Well, it has to be a diagonal line, 45-degree line on the space-time diagram. So here is my particle of light. Let's choose a different color here. Light travels forwards like that. And so this event represents the particle of light hitting the wall, which is then here on the space-time diagram. And let's call that event B. And the particle of light launched to the left travels along the space-time diagram like that at 45 degrees. but to the left. And let's call that event here, event A, okay, the light hitting the back of the train. Now let's look at it from the perspective of the observer that's moving, so that the train is moving with respect to that observer. Well, if the train is moving to the right, then that observer needs to be moving to the left on the space-time diagram. So that observer would have a t-bar axis, right? That needs to represent motion to the left. So we're not going to bend the t-bar axis this way. We're going to bend it this way, and we're going to bend it less than 45 degrees. So we're going to bend it like, say, that. So this is the t-bar axis. And whatever this angle is here, I want to bend the x-bar axis by the same amount. So it'll be something that looks like that. T-bar and x-bar. And so now we can get a sense of what the times are for the two events A and B from that perspective. Right? So they're simultaneous in one, where they're both occurring at that time according to the observer that measures space and time according to x and t. But from the perspective of the observer that measures space and time according to x bar, t bar, what we have to do is take each event and travel along the spatial axis, which from this perspective is horizontal, right? The x-axis is horizontal, so we would have to move horizontally to get the time. But from this perspective, from the t-bar, x-bar perspective, we have to move horizontal to this axis. And so that would be something like that. And so I'm going to try to be parallel to this axis. And they should have drawn those. But here I am reaching the t-bar axis somewhere up here. Let's continue this indefinitely. This event, I'm trying to be parallel to this. So I'm going to do something like that. It looks fairly parallel to this line at least, and come and meet the t-bar axis here. So these are, so first let's label this as TA, and notice that TA is equal to TB. These are simultaneous events. Here we have T bar A, and here we have T bar B. And so it's clear that T bar B is greater than T bar A, meaning that the particle of light hits the front of the train after the particle of light hits the back of the train from the perspective of the observer that's moving to the left. Right, from the perspective of that observer sees the train moving to the right. And so we can see that the events are not simultaneous as viewed by the two different observers. But they both agree that light is traveling on 45-degree lines.